Across the world, ancient civilizations left behind structures that still seem extraordinary even after thousands of years. Entire cities were laid out with deliberate precision. Massive stones were cut and fitted so tightly that the joints can remain almost invisible. Mountains were transformed into temples, agricultural terraces, and fortified settlements. And in places where water was scarce, ancient engineers created channels, reservoirs, and drainage systems that could turn difficult landscapes into functioning communities. At first, these achievements may simply look like impressive examples of ancient craftsmanship. But the more closely we examine them, the more interesting the story becomes. How did people working without modern engines, computers, industrial machinery, or digital measuring equipment plan and execute projects on such enormous scales? How did they transport massive materials across mountains and deserts? How did they calculate slopes, angles, drainage, and astronomical alignments with enough accuracy to make these structures endure for centuries? The answers are not always mysterious. In many cases, archaeologists can reconstruct the methods, materials, and organization that made these achievements possible. Yet there are also sites where important questions remain. Some structures have uncertain origins. Some abandoned projects reveal techniques we do not fully understand. And some ancient systems were so effective that later generations had to rediscover principles that their predecessors had already mastered. That is what makes these places worth investigating. Not because they prove that ancient civilizations possessed impossible technology, but because they reveal something more interesting. Human knowledge has never moved forward in a perfectly straight line. It can accumulate, spread, disappear, and sometimes return centuries later in another form. In this documentary, we are traveling across the ancient world to examine remarkable constructions that continue to challenge our assumptions about what early civilizations were capable of. From cities and temples to aqueducts, underground settlements, astronomical structures, and monumental stonework, we will follow the evidence and separate what we know from what remains uncertain. Because the real mystery may not be how ancient people could build these things. It may be how much knowledge was lost after they were gone. More than 4,000 years ago, along the banks of the Indus River, a city emerged that looked surprisingly different from many ancient settlements we imagine today. This was Mohenjodaro, one of the best-preserved urban centers of the Indus Valley Civilization, built in what is now Pakistan. From a distance, its ruins appear to be little more than sun-baked bricks and broken walls scattered across an ancient landscape. But when archaeologists began examining the plan of the city, another picture emerged. The streets were not arranged randomly. Major roads and smaller lanes followed an organized grid, intersecting at carefully planned angles and dividing the settlement into distinct sections. This was not simply a collection of houses that had expanded wherever space allowed. The city had been conceived as a system. Homes, streets, wells, drainage channels, and public spaces were placed within a broader design that suggests considerable planning. And that is where the first mystery appears. Mohenjodaro flourished thousands of years before many of the urban systems we associate with organized cities today. Its builders left no detailed engineering manual behind, no surviving architect's drawings explaining how the city was planned. Yet the physical evidence remains in the ground. The streets still reveal the decisions of people who understood that a city could be designed before it was built. But the streets were only the beginning. Beneath the surface of Mohenjodaro was a system that may be even more revealing, an extensive network for managing water and waste. Many houses were connected to drains, and wastewater was directed away from living areas through carefully constructed channels. For a civilization this old, the scale of the system is difficult to ignore. Instead of treating sanitation as an afterthought, the builders incorporated it into the architecture itself. Wells provided access to water, while covered or enclosed drains helped move waste through the settlement. In a city where thousands of people may have lived, that required more than individual household decisions. It required coordination. Someone had to determine where the channels would run, how the streets should be positioned, where water should enter and leave, and how the different parts of the city would function together. The so-called Great Bath makes the picture even more interesting. This large rectangular structure was carefully constructed and waterproofed, with arrangements for bringing in and removing water. Its exact purpose remains debated, but its design demonstrates that water management had both practical and possibly ceremonial importance. What we can see is not a modern sewer system in the literal sense. It is something much more interesting, an ancient society solving the same fundamental urban problems that every large city eventually has to confront. Here is where we need to separate the evidence from the legend. It is tempting to look at Mohenjodaro and declare that its builders possessed technology somehow centuries beyond their era. The ruins do not prove that. Archaeologists do not need an impossible explanation to account for the city's existence. The Indus Valley civilization had skilled brickmakers, organized communities, experienced builders, and a long tradition of urban development. Those facts are enough to explain much of what we see. The more intriguing question is not whether ancient people could have created these systems, but how they acquired the knowledge and organizational ability to do so across such a large settlement. Every drain had to be constructed. Every wall had to be aligned. Every street had to connect with another street. Materials had to be produced in enormous quantities and moved where they were needed. None of this happens accidentally. It requires standards, planning, labor, and some way of transmitting knowledge from one generation to the next. And yet the Indus civilization eventually declined, its cities were abandoned, and much of its written language remains undeciphered. The people disappeared from the landscape, but their infrastructure remained. That is the pattern we will keep seeing throughout this journey. Knowledge can survive in stone and brick long after the people who understood it are gone. Mohenjodaro also reveals something important about the way ancient civilizations adapted technology to their environment. The city was built in a region where water could sustain life, but where floods and seasonal changes could also create serious problems. Good drainage was therefore not merely a matter of comfort. It was part of survival. The same principle appears again and again in ancient engineering. Human beings observed their surroundings, identified recurring problems, and gradually developed systems that made those problems manageable. That is what makes the Indus city such an important starting point for this documentary. We don't need to imagine secret machines hidden beneath the ruins. The real achievement is already extraordinary. People thousands of years ago created an urban environment in which architecture, sanitation, water access, and movement through the city were connected into one functioning system. And when we look at it today, stripped of its original population and surrounded by ruins, it can feel almost modern because the problems it solved are still familiar. Cities today still struggle with water, drainage, overcrowding, and infrastructure. The difference is that our solutions are powered by technologies that ancient builders did not possess. Their solutions depended on gravity, materials, planning, and accumulated experience. Which raises a larger question. If this level of organization was possible in the Indus Valley, what was happening elsewhere in the ancient world? To answer that, we have to leave the river plains of Pakistan and climb into the mountains of South America, where another civilization transformed an environment that seems almost hostile to large-scale agriculture. In the sacred valley of Peru, the Incas carved enormous terraces into steep mountain slopes, turning difficult terrain into carefully managed agricultural land. Each terrace created a different growing environment, while channels helped distribute water through the system. From above, the landscape looks like a giant staircase descending through the mountains. But the closer you look, the more you realize that this was not simply farming on a hillside. It was an engineered response to altitude, climate, soil, and water. The Incas were not trying to flatten the Andes. They were learning how to work with them. And that becomes our next clue. From Mohenjo-Daro's planned streets and drainage channels to the terraces of the Andes, the same principle appears again. Ancient engineering was often less about overpowering nature and more about understanding it. But in the next location, that idea becomes even clearer, because the Romans found a way to move an entire city's water supply across a landscape using a force that never needed fuel, electricity, or an engine at all. They simply learned how to make gravity do the work. In the mountains of Peru, the problem was completely different from the one faced by the builders of Mohenjodaro. Here, the challenge was not organizing a city across a relatively open plain. It was finding a way to produce food on steep slopes, at different elevations, under constantly changing conditions. The Incas responded by transforming the mountains themselves. Across the sacred valley, enormous agricultural terraces were carved into the hillsides, creating long-stepped landscapes that could be cultivated where ordinary farming would have been almost impossible. The terraces did more than create flat ground. Their design altered local growing conditions, allowing each level to develop its own microclimate. Temperature, sunlight, moisture, and soil conditions could vary from one terrace to another, giving farmers more control over the environment. Water could then be guided through the system rather than simply left to run down the mountain. Standing among these terraces today, it is easy to see why they can appear almost too deliberate to be natural. Every horizontal line represents labor, planning, and an understanding of the landscape. But the most remarkable thing about them may be what they reveal about the people who built them. The Incas were not attempting to defeat the mountains. They were learning how to cooperate with them. That same principle becomes even more obvious at Moray, another Inca site located high in the Andes. From above, the enormous circular terraces resemble artificial craters carved into the earth. Layer after layer descends toward a deep center, creating a series of concentric agricultural levels unlike ordinary fields. What makes Moray particularly fascinating is the difference in temperature between the upper and lower terraces. The shape and depth of the site created distinct microclimates, allowing plants to experience conditions that were not identical from one level to another. This has led researchers to interpret Moray as a possible agricultural experimentation site, where Inca farmers could observe how crops responded to different environments before adapting them elsewhere in the empire. Whether every part of the site functioned exactly as a formal laboratory remains open to interpretation, but the physical design is undeniable. The terraces were carefully constructed, and the drainage system was capable of handling the heavy rainfall that reaches the Andes without simply turning the entire structure into a flooded basin. That matters because it reveals a recurring pattern. The ancient engineers we are studying were not necessarily using mysterious technology. They were observing nature closely, then designing systems around what they learned. And sometimes, that was enough to produce results that still look astonishing thousands of years later. Then we travel from the mountains of Peru to the Roman world, where the challenge was no longer growing food on steep terrain, but moving huge amounts of water across long distances. The aqueduct of Sigiriya is one of the clearest examples. Built to carry water into the city, the structure depended on an idea that sounds almost too simple to explain the scale of what was achieved: gravity. There were no pumps pushing water uphill. There were no electric motors forcing it through pipes. Instead, Roman engineers created a carefully calculated gradient so subtle that it could barely be noticed, yet sufficient to keep the water moving steadily toward its destination. The massive stone blocks were assembled without the use of mortar, allowing each piece to support and lock against the next. That created a structure capable of remaining stable while enduring the passage of centuries. Looking at the aqueduct today, the arches can seem almost effortless, as though the stones simply arranged themselves into position. They did not. Every level required planning, measurement, transportation, and coordination. The achievement is not mysterious because gravity itself is mysterious. It is impressive because the Romans understood how to exploit a simple natural force on an enormous scale. And once again, we see the same principle. Sophisticated engineering does not always require complicated technology. Sometimes it begins with a deep understanding of something that has been there all along. But the ancient mastery of water did not stop with aqueducts and agricultural terraces. Far to the south of the Indian subcontinent, on top of a massive rock in Sri Lanka, the builders of Sigiriya created something that combined architecture, defense, agriculture, and water management into a single complex. In the 5th century, King Kassapa I established a fortress and palace on top of the enormous rock, an extraordinary location that would have been difficult to supply under ordinary circumstances. Yet the complex included gardens, pools, reservoirs, channels, and fountains. Water could be collected, controlled, stored, and distributed through an interconnected system that allowed the summit to function as a living environment rather than simply a fortified lookout. The further you look into such places, the more the same idea appears. Ancient engineers understood that a successful settlement depended on systems working together. A reservoir had to connect to a channel. A channel had to follow the terrain. A garden needed water. A building needed drainage. A city needed all of these things at once. Sigiriya therefore becomes more than an impressive palace on a rock. It becomes another example of ancient planners treating the landscape as part of the machine itself. Instead of bringing modern infrastructure to nature, they shaped natural forces into infrastructure. And that may be the most important lesson from this part of the journey. When we look at ancient engineering through modern eyes, we sometimes expect to find a missing machine that explains everything. But the evidence often points somewhere else. The technology was in the landscape itself. Gravity moved the water. Mountains created differences in climate. Rivers supplied cities. Slopes became agricultural fields. Rain became something to collect rather than something to fear. The ingenuity came from understanding these forces well enough to design around them. Mohenjodaro organized water and waste within a city. Inca engineers adapted mountains for agriculture. Roman engineers turned gravity into a transportation system for water. The builders of Sigiriya created an integrated hydraulic environment high above the surrounding landscape. These civilizations lived thousands of years apart and belonged to very different cultures, yet they repeatedly arrived at the same fundamental idea. The environment is not simply an obstacle. It can become part of the solution. But if ancient societies could engineer water, soil, and terrain with such precision, another question begins to emerge. What happened when they turned their attention away from the ground beneath their feet and toward the sky above them? The ancient world was not only concerned with controlling the ground beneath its feet. For many civilizations, understanding the sky was just as important as understanding rivers, soil, and seasons. The movement of the sun could determine when crops should be planted. The moon could mark the passing of months. Certain stars appeared at particular times of year, providing a reference point for communities that had no clocks or modern calendars. Across Mesoamerica, the Maya developed an especially sophisticated relationship with the heavens. Their cities contained temples and structures positioned in ways that allowed priests and astronomers to observe the movement of celestial bodies across the horizon. The sun, moon, Venus, and the stars were not merely objects in the night sky. They were part of a system used to organize agriculture, rituals, and political life. The important point is not that the Maya possessed some mysterious technology. Their knowledge came from something far more recognizable: observation repeated over generations. A single observation could be forgotten. Thousands of observations, carefully recorded and passed between specialists, could become a science. But that science was fragile. When cities declined and texts were destroyed, much of the accumulated knowledge disappeared with them. What survives today may be only a fragment of what ancient Maya astronomers once understood. That same fascination with the sky appears in Europe thousands of kilometers away, where Stonehenge still stands on the Salisbury Plain. The monument was built over many generations, beginning roughly 4,500 years ago, and its massive stones were arranged with deliberate attention to the movement of the sun. The largest sarsen stones weigh many tons, yet they were transported, raised, and positioned with enough precision to create a structure whose geometry still attracts astronomers and archaeologists. Horizontal stones were fitted onto vertical uprights using woodworking-style joints, an approach that reveals careful planning rather than random placement. The exact purpose of Stonehenge remains debated. It may have served ritual, ceremonial, astronomical, or social functions, and it may have served more than one purpose over the centuries. What we can say with confidence is that its builders were willing to invest enormous amounts of labor into creating a monument whose orientation had meaning. That alone tells us something about the society that built it. Someone had to understand where the sun would appear on important days. Someone had to mark those positions. Someone had to transmit that knowledge to the next generation. And when the stones were finally arranged, they created a permanent calendar written not on paper, but into the landscape itself. Yet Stonehenge was not the first prehistoric monument to connect architecture with the movement of the sun. In Ireland, Newgrange was constructed more than 5,000 years ago, making it older than the Great Pyramid of Giza. At first glance, it appears to be a large grass-covered mound, but inside is a carefully built passage leading to a central chamber, and above the entrance is a narrow opening known as the roof box. During the winter solstice, the rising sun reaches the entrance at exactly the right angle for a narrow beam of light to pass through the opening and travel deep into the chamber. For only a brief period around sunrise, the darkness inside is transformed by sunlight. The effect is so precise that it cannot be explained by chance. The builders had to understand the relationship between the structure and the position of the sun at the winter solstice, then preserve that alignment for generations. Even more remarkable is the roof itself. The chamber has remained remarkably watertight for thousands of years, despite being constructed long before modern concrete, sealants, or waterproof membranes. Newgrange reminds us that prehistoric engineering was not simply about lifting stones. It involved orientation, geometry, construction methods, and a patient understanding of cycles that repeat year after year. The monument did not merely observe time. It was built around time itself. Then, on the other side of Europe, another prehistoric site offers an even older glimpse into the same relationship between architecture and astronomy. The Goseck Circle in modern Germany was constructed roughly 7,000 years ago, making it considerably older than Stonehenge. The monument consisted of concentric ditches and wooden palisades, with openings arranged to mark particular positions of the sun around the winter solstice. Its builders had no written mathematics, no modern surveying equipment, and no precision instruments in the modern sense. Yet they created alignments that suggest careful observation of the horizon and the annual movement of the sun. Even further east, at Kokino in what is now North Macedonia, natural rock formations were adapted into an astronomical observation site where markers and sightlines could have helped people track the movements of the sun and moon. These sites do not prove that prehistoric societies possessed a formal astronomy identical to ours. They reveal something more basic and perhaps more impressive. People were capable of creating reliable systems from repeated observation. They could watch the horizon, recognize patterns, compare one year with another, and preserve those patterns in physical structures. The sky became a clock long before mechanical clocks existed. And once that knowledge was embedded into architecture, it could survive far beyond the lifespan of the people who first discovered it. This brings us back to the larger pattern emerging across the ancient world. In Mohenjodaro, people organized water and waste. In the Andes, engineers transformed steep mountains into productive landscapes. Roman builders used gravity to carry water across enormous distances. At Sigiriya, hydraulic systems allowed life to flourish on top of a massive rock. And now we are seeing something different but connected. Ancient societies were also measuring the sky, tracking the seasons, and turning celestial cycles into calendars and monuments. None of this requires forgotten machines from another age. It requires something both simpler and more demanding: observation, patience, mathematics, and the ability to preserve knowledge across generations. But knowledge can be fragile. A city can be abandoned. A language can disappear. A library can burn. A civilization can collapse, leaving behind only the physical structures of what it once understood. And that is where the story becomes more complicated. Because the next discoveries are not just about what ancient people could calculate or build. They are about what they could do with materials that modern observers often assume were beyond their reach. Massive stones, hardened metal, structures so large that even today, moving them would require extraordinary effort. And once we reach those sites, the question changes again. How far could ancient engineering really go? There is a point where ancient engineering stops being mainly about design and starts becoming a question of scale. A wall can be precise, a canal can be efficient, a temple can be aligned with the sun. But what happens when the material itself becomes the problem? In China, the Yangshan steel offers a remarkable example. During the Ming Dynasty, Emperor Yongle ordered the creation of a colossal monument in honor of his father. Instead of simply transporting finished blocks, craftsmen began carving enormous shapes directly into the mountain. The surviving stone surfaces show deliberate geometry and carefully worked faces, but the project eventually encountered a problem that no amount of ambition could easily solve. The pieces were simply too massive. Transporting them to their intended destination would have required an extraordinary logistical operation, and the project was abandoned before the monument could be completed. The unfinished stone remains exactly where the workers left it, offering something rare in archaeology, a record of an enormous project that was attempted but never fully realized. It reminds us that ancient engineers did not always succeed. Sometimes the ruins preserve not a triumph, but the moment when human ambition finally met a physical limit. That question of scale becomes even more difficult when we look at the massive stonework of Baalbek in modern Lebanon. The Roman sanctuary is famous for enormous blocks incorporated into its monumental platforms. Some of them weighing hundreds of tons and, in certain parts of the complex, reaching extraordinary dimensions. Later observers naturally began asking how ancient builders could possibly have transported and positioned such material. Ramps, rollers, sledges, cranes, and large labor forces have all been proposed in different contexts, and some methods are known to have been used by ancient builders elsewhere. But the surviving evidence does not provide a single simple explanation for every block at Baalbek. That distinction is important. The presence of huge stones does not prove the existence of unknown machines. It does, however, force us to take ancient logistics seriously. Quarrying is only the first step. Once a stone has been cut, someone has to move it, guide it, raise it, and place it accurately. The larger the block becomes, the more difficult every stage becomes. At Baalbek, the stones themselves are evidence of a problem that ancient engineers were willing to solve on a monumental scale. And sometimes the most fascinating part of an ancient construction is not the finished building, but the chain of decisions required to make the impossible-looking object stand exactly where it does. The Andes offer another version of the same challenge, but with a completely different solution. At Sacsayhuaman near Cusco, enormous stones form walls whose individual blocks were shaped to fit against their neighbors with remarkable precision. There is no regular rectangular pattern. Instead, each stone has its own unique outline, almost like a three-dimensional puzzle. That irregularity is part of the engineering. By creating a wall in which blocks interlock rather than simply stack, the builders produced a structure capable of tolerating movement. In a region where earthquakes are a constant threat, that matters enormously. The wall could flex without immediately collapsing because there was no single straight seam running through the entire structure. The impressive part is therefore not simply that the stones are large. It is that the builders understood the behavior of stone under stress well enough to shape every block around that knowledge. This is a very different kind of sophistication from modern engineering. There are no computer models on the site, no digital simulations, and no steel reinforcement hidden inside the walls. The solution is visible in the stones themselves. Once again, the physical evidence gives us more than a mystery. It gives us a record of accumulated experience. The builders may not have described structural dynamics in modern mathematical language, but their walls demonstrate that they understood something about them. The same principle appears in places where the entire landscape was turned into architecture. At Kailasa Temple in India, artisans did not build a monument by assembling blocks one on top of another. They removed the mountain itself, beginning at the top and cutting downward until an enormous temple complex emerged from the rock. This method created an extraordinary problem. Every cut was permanent. If a mistake was made while carving, there was no easy way to add the missing stone back. The project therefore demanded planning long before the final form became visible. The scale of the excavation was enormous, with hundreds of thousands of tons of material removed to create the finished complex. Similar questions arise at the rock-cut churches of Lalibela in Ethiopia, where entire churches were carved vertically into volcanic rock, or at the Barabar caves in India, where interiors were polished to an astonishing degree. These places show another category of ancient engineering, subtractive construction. Instead of bringing materials to a design, the builders removed everything that did not belong. The mountain became the raw material, the structure, and the final monument at the same time. And once the carving began, there was no second attempt. Every surface represented a decision that could never be reversed. Perhaps the most useful discovery in this entire investigation is that ancient engineering rarely depended on a single extraordinary trick. It was usually a combination of ordinary principles applied with extraordinary discipline. Weight could be managed through ramps and leverage. Water could be moved through gravity. Stone could be stabilized through geometry. Buildings could be adapted to mountains instead of forcing mountains to fit the building. 'T' What looks miraculous from a distance often becomes understandable when we examine the individual problems one at a time. But that does not make these achievements ordinary. The knowledge required to coordinate thousands of workers, extract materials, transport them over difficult terrain, maintain consistent measurements, and preserve techniques across generations was itself a form of technology. And when the societies that possessed that knowledge declined, parts of the system could disappear with them. That is why abandoned monuments are so valuable. They preserve not just what ancient people achieved, but the traces of the methods, choices, and limitations behind those achievements. Yet there is one final category we have not examined closely enough. What happens when an ancient structure cannot be explained simply by its size, its materials, or its engineering? What happens when the very purpose of the monument remains uncertain? In the final chapter, we move into that territory where architecture, astronomy, ritual, and lost knowledge begin to overlap. After traveling across cities, mountains, deserts, temples, aqueducts, and underground chambers, a pattern begins to emerge. The most interesting thing about these ancient structures is not that they look modern. Many of them do not. They belong unmistakably to the worlds that created them. What makes them remarkable is that their builders repeatedly solved difficult problems with a level of organization that can be easy to underestimate from a modern perspective. Mohenjodaro created an urban system in which streets, wells, drains, and public spaces were connected. Inca engineers transformed steep mountains into productive agricultural terraces and developed hydraulic systems adapted to changing elevations. Roman builders learned to carry water over enormous distances by carefully controlling gravity. Ancient astronomers watched the sky long enough to turn repeating celestial movements into calendars, rituals, and monumental alignments. Elsewhere, builders shaped massive stones, carved entire temples from mountains, and created underground environments capable of supporting large communities. None of these achievements requires us to imagine that ancient people possessed technology from another world. But they do require us to abandon another assumption, that the past was simply a primitive version of the present. Ancient societies had their own systems of knowledge, and many of those systems were far more sophisticated than the surviving evidence initially suggests. One reason this knowledge can seem mysterious today is that we often see only the final structure. We see the aqueduct, but not the generations of builders who learned to work with slopes and water. We see the Inca terrace, but not the farmers and engineers who experimented with soil, drainage, and altitude. We see a monumental stone wall, but not the countless decisions that determined which block should be cut first, how it should be moved, and where it should be placed. The finished monument hides the process that created it. That is where archaeology becomes so important. A structure is not simply an object. It is a record of decisions. Tool marks can reveal how stone was worked. Drainage channels can reveal how water was expected to behave. The arrangement of streets can reveal how a city was organized. The orientation of a monument can reveal what its builders were watching in the sky. And when several different pieces of evidence point in the same direction, we begin to reconstruct a system of knowledge that may no longer exist in written form. Sometimes the system is understandable. Sometimes it remains incomplete. But either way, the evidence reminds us that intelligence does not disappear just because the people who possessed it do. The more unsettling question is what happens when that chain of knowledge is broken. Civilizations do not collapse neatly. Cities are abandoned. Political systems disappear. Languages change. Religious traditions fade. Wars destroy archives, buildings, and workshops. Skilled craftsmen die without passing every technique to another generation. A technology that once seemed ordinary can become difficult to reproduce simply because the network of knowledge supporting it has vanished. We can see hints of that process in sites that were abandoned for centuries and later rediscovered by people who no longer understood their original purpose. The ruins become mysterious because the explanation disappeared before the structure did. That is why a site can survive physically while its meaning becomes almost impossible to reconstruct. Even the ancient Maya, whose observations of the heavens were recorded with remarkable care, lost enormous portions of their intellectual tradition after their cities declined and their texts were destroyed. Across the world, the same basic pattern appears again and again. Knowledge survives only when someone continues to use it, teach it, record it, or preserve the institutions that support it. Without that chain, even highly developed expertise can become a forgotten fragment buried inside a monument. There is also an important lesson in the discoveries that initially appear the most mysterious. When we examine them carefully, the answer is often less dramatic than the legend surrounding them, but more impressive because it is human. The great engineering achievements of the ancient world did not happen because ancient people ignored physical laws. They happened because they understood those laws through observation and experience. They knew how water moved downhill. They knew that certain shapes resisted pressure. They understood that some materials behaved differently from others. They recognized patterns in the sky and repeated measurements until those patterns could be used. They developed construction methods through trial, failure, improvement, and memory. Modern engineering has transformed those principles with mathematics, computers, machinery, and industrial materials. But the underlying human process is surprisingly familiar. What looks like an ancient miracle may therefore be something more meaningful. Evidence of generations of people patiently accumulating knowledge without leaving behind the textbooks we depend on today. And perhaps that is why some ancient structures feel so strangely modern. We recognize the logic inside them even when the civilization that developed it is gone. So perhaps the biggest mistake would be to ask whether ancient civilizations were somehow ahead of us. They were not traveling along the same technological path we followed, and their achievements cannot always be compared directly with modern engineering. The more useful question is what knowledge they developed for their own problems, and how much of that knowledge survived. A hydraulic system in the ancient world was designed for a particular climate. A mountain terrace was shaped around a particular landscape. An astronomical monument reflected the needs and beliefs of a particular society. A defensive wall responded to a particular threat. Each solution belonged to a specific context. Yet when those civilizations disappeared, some of their solutions became difficult to understand or reproduce. That is the real mystery behind the ancient world. Not aliens, not lost super technology, not impossible machines hidden beneath the earth. The mystery is more human than that. Civilization can build extraordinary things, then forget how much effort and knowledge made them possible. What survives may be a wall, a road, a canal, a temple, or a city of stone. But behind every structure are generations of people whose names history never recorded. They learned things, improved them, passed them on, and eventually disappeared. The monuments remained. The knowledge became fragmented. And perhaps that is the final lesson these ancient constructions leave us with. Progress is not always a straight line upward. Sometimes it moves forward, sometimes it stops, and sometimes it turns back toward something humanity once knew and has to learn again.